Hello everybody, and welcome back to my basement for part 2 of example 7. So in part 1, we went over the beginning of this handout describing data manipulation, setting up the story for the analysis, and the main story can be summarized by this table right here. We're going to be examining the interaction between a 2-group version of gender and a 3-group version of dementia. This is what would be known as a two-way analysis of variance. And the adjusted means, holding all of the other model predictors at their zero values, are shown in this table, in which these terms that are unique combinations of each particular combinations of groups are known as cell means, and out here are what's known as marginal means, averaging over the unique combinations and treating them as equally weighted in this case, as is typically done. So the previous example that we went through was looking at how you tell SAS or Stata how to get all of the information that you would need to describe the patterns of this interaction when you have done all of the coding yourself to distinguish one group from another. So we had a gender variable that is a 0, 1 that we're treating as a quantitative predictor, and we created codes for dementia group that were 0 and 1 values to distinguish the future group from the none group and the current group from the none group, and then we put in the interaction terms. And what we saw out of the results summarized in the first video, all this stuff we talked about there, is we got all possible simple effect comparisons. So how the gender difference, for instance, differs in this group versus that group, how the dementia group difference differs in men from in women, and all of those differences are summarized down here in terms of the pairwise effects as well as the differences in the pairwise effects, or what I would call an interaction single degree of freedom contrast. Foreshadowing what we're going to see when we fit the same model a different way, letting the program do the coding, is some of these effects are going to become marginal. And so distinguishing when the program is giving you something marginal from when it's giving you something that's conditional on a 0 value of the interacting predictor takes some practice. And so that is what I am here to help you get. So this example is starting on page 7 of example 7. And I am changing the coding of the model by letting SAS do the coding for me. So Stata as well. So here's the big difference in what's going to create all of the subsequent differences in what the coding and the interpretation looks like. The use of the class statement to get SAS to understand that dem group is a categorical predictor that needs contrasts. The analog, by the way, in Stata is the use of I dot instead of C dot in front of dementia group. And in Stata, I have set this up so that the same output will be obtained in both programs by changing the reference group for who is the reference point for the intercept to be the last highest group, ref equals current, because that is what happens when you put dem group on the class statement. So let me flip back to lecture 7 for just a second and remind you of what is happening internally. So this is an example on this slide of a 4-group variable. When you use the class statement in SAS or the I dot prefix in Stata, what's going on internally is that it is creating new dummy-coded variables, one for each possible category. So in this example, I have created the names that would go with what these would be interpreted as. But the key here is that there's as many of these internal contrast variables as there are groups. And you can't have all of them in the model if you have a fixed intercept because one is redundant. So the question is which gets left out. And what happens in SAS is that the highest gets left out, such that the highest group then becomes the reference given the coding pattern of what's left. What happens by default in Stata is that the first one gets left out, creating the first one as the reference group, giving the coding pattern for what's left. So what's important to note is that everywhere in the code where you are referring to the original categorical predictor, so for instance, group on this slide, you have to tell it what then to do with all of the internal contrast variables it has created to represent the full effective group. And so that's why the code looks different. In this case, all these zeros and ones that go after dem group are filling in the values that correspond to those internal variables. So because the reference group has changed to be the last group, I have changed the description of in the model equation accordingly. So now I have CN and CF as my variables because current is the reference, and each of the other groups is going to be compared to current instead. And so the same thing happens in the interaction terms. In the code, the previous dem NF and dem NC variables, or what would be CN and CF in this case, have been replaced by dem group. So dem group is all you need for the main effect, and then sex by dem group is the interaction. So even though this is easier to write and it looks more straightforward, I don't like starting from this point because it is difficult to ascertain just from this code that this is actually two things you're asking for because there's three groups, and this is actually two things you're asking for because there's three groups. So it doesn't correspond as directly to the linear model representation as it does when you do the coding yourself. The first contrast here that is going to lump together my two new interaction terms is actually redundant with what shows up on your default output. So when you denote a categorical predictor on the class statement in SAS, it understands that you want to lump together the contrasts to be able to get an overall effect of that predictor variable, or what's known as an omnibus effect in a ANOVA type language. So I didn't have to write this, but for comparison with the other models and to show you what it would have looked like in case you ever need to ask for something like this, I went ahead and included it. And so note that we're listing the two interaction terms, but after each, I have a pattern of zeros and ones because I have to tell it what to do with each of my internal contrast variables. So what this pattern right here of -110 is saying is contrast the interaction of gender, how the effect of gender differs between the none group, which is still first, and the future group, which is still second, and leave out current. And now do it for the none group versus current. I could have done it for future versus current as one of these. It doesn't actually matter because once you have two of them, the third is a linear combination. So they just have to be two different contrasts. I then am showing how to get the simple effects of dementia that are lumping together the two contrasts within each gender that would delineate the three dementia groups. So it's the same pattern that we went over in the last video, and by we, I mean me, where that's one thing. So the comma happens at the end. Terms that do not have a comma separating them are going to be added together. So this is the difference between none and future, and it's the difference specifically in men because multiplying by gender when gender is 0 would zero everything out. Likewise, this is none versus current. Down here is how you would get to the simple group difference for women. So it's none versus future, but then if gender is 1, then multiplying by a 1 carries that same pattern forward. So these are, this is something that your output would not include by default because it's a linear combination of parameters, whereas this is something that you would get by default because it is for the reference group, and gender right now is still being treated as just a regular quantitative variable where we're holding things at 0. The use of the class statement allows you to add this, so this is something new. LSMeans is only for variables that are on the class statement. What I'm asking for, it stands for least squares means, is going to be the mean for each of my dementia groups. This is going to be an adjusted mean, holding other things at particular values. And what it is adjusted at is given right here. So the at controls which quantitative predictors are conditioned on and what their values are to be. So the list given in parentheses corresponds to the list of these values. So for both of these lines, I'm holding age at 85 and grip at 9, so that's the first two zeros. But then I'm conditioning on men as the 0 here and women as the 1 here. So this is going to give me 3 means, 1 for each group for men, 3 means, 1 for each group for women. I am asking for all possible simple effect differences, as well as the standard errors and the t-values and the p-values that go with those differences. Oddly, some of those are not provided by default, even though you would need to report them. So these two lines right here that give me all possible pairwise differences between dementia groups for each gender are actually redundant with this output. So I have saved these 6 lines of code, replacing them with these 2 LSMeans lines. What I haven't gotten yet are the sex differences that are conditional for each dementia group. So we need to ask it for what variables are we trying to get the simple slope for, and then tell it for what group we want those simple slopes. So the main effect of dementia is zeroed out here because it's not relevant. We're asking for a gender difference as the thing to be estimated. So in each line, we start with the gender difference given by the model because that's what we need at a minimum. Then who is it for? The 1 says which group that it's for. So you can think of this as like a switch, like 1 for this group, 0 not for that group. And then the last part of this here, these are partially redundant with your model output, but they're included here to show you that we end up with the same idea, that there's 3 possible interaction contrasts, and each one can be interpreted 2 different ways. So where these come from, part of the reason why I've repeated this simple effects of dementia group, even though it's redundant with up here, is so that you can see the logic of where these things come from. For instance, if we have the sex effect differing between none and future, we could focus on, say, that line minus that line, so line 2 minus line 1, or we could think of it the other way and have this line 2 minus that line 1, and we would end up with the pattern that we have right here. So the differences between the group differences are given by subtracting the reference line from the line that is given by for the alternative group. But key to understanding this code is understanding that by each of these variables here, you're telling it what to do with each group at all times. Turn it on, turn it off, or ignore it. So 1 means turn it on, 0 means ignore it, and a combination of -1 and 1 means compare it. In Stata, it is the same except for this IB last that controls what the reference group is. I'm changing it so that the output matches SAS. Contrast is a statement we have not yet seen in Stata. This is lumping together the contrast for the interaction, and that's not something it provides by default. It's something that you do need to ask for, but it's easy to ask for it because it understands you're asking for all possible interaction contrasts given by this combination, so 2 of them in this case, that create 3 different interaction contrasts, 2 directly, 1 is a linear combination. We have the test statements here that are giving us the simple effect of dementia lumped across the 2 contrasts for each gender. And so the same idea, this is all one thing. So this describes how you would ask for a group difference of the 1 group and a group difference of the 2 group. So in this case, 3 group is the reference. And so you're saying put 1 equal to 3, so make it not allowed to be different. And then make 2 not allowed to be different either. And then for women, the same idea holds, but you're also combining the effect of the interaction. So to get to what it is for women, it's what is the difference in men, what is the difference in the difference for women. You put those together, you get what it is for women, and then the equals 0 says, no, don't allow it to be different. So it's like, what if there was no differences across the 3 dementia groups in women? That's what this combination is going to get at. And tests like contrast is going to give you F-tests that give you the significance tests, but not the effect sizes that correspond to them, unfortunately. To get adjusted cell means, margins, our friend that we've met before, simplifies even further. So now I can say, hey, I.dem group, that means give me all the group means and condition on age and group at 0, but give it to me for a range of values for the gender covariate, treated as a quantitative variable. That's why I'm saying covariate. And if you want some plots, that's always helpful. Margins can also be used to create differences between groups. So in this case, I'm asking for means and then the differences to make sure that I've got all of those. And then means for dementia group holding gender at 1, and PW compare means all the differences. And then we can have the simple effects of gender conditioning on each group. And so that is not redundant with margins. However, all of these pairwise differences between dementia groups conditioning on sex are redundant with margins. So all of this code can be replaced by just that much. And then last but not least, we still need the interaction contrasts, which are not given to us otherwise, not all of them anyway. So we can talk about how the gender effects differ between dementia groups, how the dementia group effects differ between genders. And these patterns of -1s and 1s come about as taking each of the alternative groups in the comparison and subtracting from it the line for the reference group in the comparison, same as before. I have omitted the model test in R-squared because this is the same model that we saw in the first part of this example. It's just a different way of asking for the same information. So I want to highlight the differences that happen when it understands that DEM group is one thing that needs to be represented by 2 contrasts, and it does so using 3 internal variables to do so. So this is SAS output, but we get similar patterns in Stata. You can look at what the Stata output would be in the zip folder I posted online that goes with this handout. So the main effect of sex here, because we are interacting it with DEM group, SAS is marginalizing. So this is not the gender effect in any specific group like it was before. It is on average across the 3 groups. It is also now marginalizing over the interaction term, and it is marginalizing over dementia group. However, this is specific to men because it is not marginalizing over gender yet. That's going to happen in the next model. So it's very tricky to figure out what's marginal and what's conditional. I'll say it again. This is marginal. This is the main effect of gender because SAS understands it needs to marginalize over DEM group. This is conditional because it is specific to the interacting predictor, which is being treated as quantitative, being 0. We have let's see here, we have the effect sizes that go with that here. These are things that SAS provides that Stata do not. And then these are the results of the contrast, getting at the overall omnibus effect for the interaction, which is already generated for us. So that's the same thing that's given up here, as well as the simple main effect of dementia for men that we asked for was also generated for us up here. So the one that was not generated was the simple main effect for the non-reference group because it doesn't understand that gender needs something to be marginalized over. I have noted on the table of fixed effects here what things have changed and what things haven't. So the intercept now has changed. It is specific to the current group rather than the none group, and that's why it's so much lower. Age, group, and their interaction are the same because they are not involved in the sex by dementia interaction that we're pulling apart here. Likewise, this gender difference has changed because it is for the current group now instead of the none group. And these dementia group differences are different because they are relative to the current group, and the interaction terms are also different because they are relative to the current group. But within this, we can still go about the same pattern. This is the dementia group difference, or excuse me, this is the main effective sex conditionally in the current group. This interaction term tells us it is less negative by 7 in the none group. And this interaction tells us that the gender difference is less negative or smaller by 8 in the future group. So now what we don't have is none versus future. The difference between these two would have to be a linear combination. And you've noticed that there's some extra stuff in here. So the group that is the reference is denoted explicitly as such as the group that is zeroed out here. So you might see this and look at the zeros and dots and go, wait a minute, did I screw something up? No, you did not. That's just SAS's way of trying to help you out by telling you this is the internal contrast variable that I zeroed out, did not include because it was redundant with the intercept. Therefore, you can interpret all the other contrasts against it as the reference. And note that the labels here showing up are a function of the fact that I used labels to attach them to dem group in the very first step, so created them in proc format and attached them to dem group for this reason, so that my output would be easier to follow in the case of multiple groups. The other thing here is this B, that it gives you this what looks like an error message, but it's not. It's telling you the matrix has been found to be singular. That means that if it had included all of the internal contrast variables, that it would have a problem because one is redundant. And so it fixed it by kicking one out, and it's reminding you which terms are conditional, which is very helpful. I wish it did that reminding on regular output, but it only does so on output involving categorical predictors. So here is my translation. It's not a problem. It's just what is needed to be able to get to the unique solution. Now here comes some different output. So just to recall, we had a new command that we hadn't seen before, LSMeans, that allows us to ask for all groups and all group differences, conditioning on whatever continuous or quantitative predictors that we feel like. And so the output from that is right here. So this gives us the adjusted group means conditionally for men when sex is 0, and then it builds this matrix to do all possible pairwise comparisons. So the values that you're given here are actually the t-tests and the p-values. It doesn't actually give you the differences, which is annoying, and I couldn't find a way to make it give you the differences. That will not be the case when we get to proc mixed, by the way. They give you the differences directly. Likewise, here are the group differences, group means for gender equals 1 for each of the dementia groups, and then here are the group differences. And so then we get to the table that is generated by all of the estimate statements. These are new, so these are the differences between men and women, the simple effects of sex, conditioning on each group. These are redundant, so these group differences that I asked for via estimate statements are giving you the same information as these tables. The only difference is that the actual differences are given here in the first column in addition to the t-values and the p-values, which I find helpful. And last but not least, the differences in the simple effects. These are interactions and they are not given above. So more specifically, in the table, 2 of them are comparing the current group to each of the others. And so that is these 2, which are backwards in sign because the current group is not the reference in this coding scheme that I used to create these statements. And the one that is missing is difference between the none and future groups in this case, which is given right here. So, summarizing, when you have denoted one of your predictors as categorical. So I dot in stata dem group in SAS on the class statement. Everywhere in your code, you have to tell it what to do with those internal contrast variables that it is creating. But you can ask for each group mean and group differences much more straightforwardly. As before, though, only 2 of the interaction contrasts are given, and you have to be able to ask for any more than that are linear combinations. All right. Last but not least, so picking up on the last version of this model, starting on page 10 of example 7, what happens if we were to treat both of my categorical predictors as categorical in the program? So sex now, it was coded 0, 1, such that men were the 0 and women were the 1. By putting it on the class statement, so doing this for demonstration purposes, how would this code need to change if you wanted to have an interaction between 2 variables being treated as categorical? It is actually going to make it backwards. So even though you coded it 0, 1, it's going to go in and build its internal contrast variables and kick out the highest one, which will create that highest group as the reference. So functionally, it just reversed your coding. Women are now the reference group and men are the alternative group. So what started out as 0, 1 is now 1, 0. And that's why I have renamed it WM, for women as the reference and men as the alternative group. Just like it did before when it coded up dementia group as a categorical predictor, the highest becomes the reference, and so it's C current is the highest versus N, and C versus F. And the same thing happens in the interaction terms as well. So the code looks similar in terms of the model. We've added gender and dementia group to the class statement, so they're both having internal contrast variables created for them. And dem group is still here and the interaction is still here. So this is still 2 things because there's 3 groups. This is still 2 things because there's 3 groups. By things, I mean fixed effects. The contrast statement for the test of those 2 new interactions is redundant with what is going to be generated by class, but just to show you what they look like. This pattern. Internal contrast variables now are being used for both of these predictors. So what you are telling it with this combination is what to do with the combination of cells. The 2 by 3 table that defines each unique combination has to have a value now. So this is a bit of a headache and why I tend to avoid this specification if at all possible. How do you know what the order is? It's based on the order on the class statement. So it cycles through all of the second group for the first level of this variable, and then all of the second group for the second. So this coding is right here. It's men, none, men future, men current, women none, women future, women current. Then we get into where the hell did these numbers come from? That's a great question. So the idea of an interaction is different differences. It is how say the difference between none and future varies between men and women, or the difference between none and current varies between men and women, or things like that. So I just need to provide 2 sets of those different differences to describe what the interaction term is, and all of the others are linear combinations. So the first part of this right here, that is setting up one of my differences as none versus future in men. Then this one is going to be none versus future in women. But because I need the difference of the differences, it's like I have to take this set and subtract that same pattern for what it would be for women, which flips the sign. So that's why the sign has an opposite pattern, is because there's an implicit minus sign of one term minus the other. And the same happens here. This is none versus current as one of the contrasts. If I took that pattern and subtracted it for women, it flips the pattern of the signs. So this takes some practice. It will become a little more clear possibly when you see the rest of the code down here. So we're saving predicted outcomes. We're asking for marginal means for gender. So we're asking it to give me the, we're averaging over dementia group in this case. I'm doing this for pedagogical purposes, not because it's useful. And here we're averaging over gender. And then we're getting the combination of the two. So this is going to give us the cell means. It's going to give us all pairwise differences holding these covariates constant 0. And there's something new here. So slice means per. So what slice equals dem group is going to give us the main effect of gender specifically for each dementia group, which is redundant with pairwise differences since gender is only 2 levels. But this one is going to give us the differences across the 3 dementia groups, a 2 degree of freedom test per gender. So that one is what I normally had to ask for via extra contrasts, but it's going to be computed directly via this slice option. So slice is a really nice tool for asking for simple effects within each level of the interacting variables. I have been unsuccessful at getting it to extend to 3-way or higher level interactions though. Here we go then. So this right here, this is the sex differences within each dementia group. This is redundant with what we would get from this LSMeans slice equals dem group. Then we have the dementia group differences specifically for gender. And so note the patterns of the zeros and ones out here. There is an option that you can add to any of these statements, /e, that is going to generate a table in your output that has the list of what each cell belongs to and the value that you assign to it. So that way you can actually check who is getting the -1, for instance, and who is getting the 1. The table ordering is the same all the way down, so you only need one check, and then you can deduce where the ones and zeros are going for everything else. But notice if we're talking about sex differences, that's a difference here of -1 versus 1 for the 2 groups. And then that pattern gets multiplied by this pattern to create what happens out here. Note the order that I found by using this check E /E statement. The dementia group differences here. So this is none versus future. This is none versus current. This is future versus current. Then multiplied by sex being irrelevant. 4 men or 4 women give us the pattern that's out here. And then we get to the interaction contrasts. So it's the same case to where if we take, say, this line and subtract from it that line, then we end up with this combination here. So these possible different interactions, there's 3 of them that are possible. I listed 2 of them up here to get the contrast statement to demonstrate how to get it. So this is kind of a pain in the ass. Figuring out this many zeros and ones is very challenging, and so this is my least preferred way of specifying interactions. If I have a categorical predictor and I need to interact it with another categorical predictor, I will usually try to code one of them so that at most I only have 1 dimension's worth of zeros and ones to fill in. Stata then has a lot of the same features to where we have contrasts to give us the marginal effects of dementia and the marginal effects of gender that are provided by default when you use class and SAS, as well as the interaction term. I'm asking for marginal means for gender and for dementia group. Note the as balanced. That means it's treating the groups equally in averaging over them. Alternatively, you could create weighted means based on the per group sample sizes, but that's not what SAS is doing, so I'm trying to keep everything the same across programs. Then we get into the adjusted cell means and their differences, as well as the analog to the slice type statements. So this here, margins, I want the differences across sex for each dementia group, and then this one does the opposite, differences across, let's see here, differences across, all right, I'm trying to remember how I did this here. Okay, this one is to make the picture. Okay, this one is simple of effective sex per dementia group. So this is the analog of slice, the ordering behind this at sign. If you flip the order, then you get it the other way. It's the effective dementia group per uh, uh, gender. And then the interaction contrast, in order to break those into specific pieces, you need the same sort of pattern of zeros, ones, and minus ones that we saw up here. So very tricky. If you get the pattern of which is the negative and which is the positive wrong, you'll still get the same test, but the direction of the difference will be backwards. And then in terms of SAS output, so previously this effective gender given here was marginalized over dementia group. Now this one is marginalized over gender, so this is new in terms of what it represents with the corresponding effect size. Let's see here. I think I may have left off a piece. I think I left off a line of code here for a contrast. I'll have to go back in and add that. So I didn't go to the trouble to ask for these things. I need to look at this giant table. So this describes the change in the coding of gender that results when you put it on the class statement or denoted as categorical. Now the highest group is the reference. So even though it was 0 men, 1 for women, it's functionally backwards. The 0 group that has been removed from the internal variables is the women group. So that means men are the alternative group now. Hella confusing, I know. The current group is still the reference, as you can tell, and so that's why the things that are zeroed out here are the way that they are. But this gives you the sense that there are multiple possible interaction terms and you're only getting 2 of them. There should be a third that is a linear combination with the same error message up here. Okay, so then how do we use the information to actually talk about the interaction? So here is what is traditionally focused on in teaching these models from the lens of an analysis of variance, is that you would get marginal means. So this is the mean of men averaged across dementia groups. This is the mean for women. And you get a test of those differences in means. Here are the marginal means for dementia group averaged across gender, and then we get the p-values for these tests. And so these to me are exceedingly unhelpful because they do not tell us anything about the interaction term, and they also don't really tell us, like, these means don't apply to any particular people. They are averages across groups of people, and the whole point of the analysis is trying to figure out how groups differ from each other. So this traditional marginal means and mean differences, I think, is useless. Then we get into the cell means, and I asked SAS to give me all possible pairwise differences between the 6 cell means, but only some of those are going to be relevant in understanding how the simple effect of one predictor varies as a function of the other as a moderator. So that's not really helpful either. So if we go back to our original table here, traditional ANOVA output gives us our marginal means as well as our marginal mean differences, but it doesn't tell us anything about how each of these simple effects differ as a function of the moderating variable. So that's where we need to ask for other information. So these are the results from using slice within LSMeans, where what this term is the gender difference specifically within the none group, specifically within this group, specifically in this group, as well as the corresponding effect size, which is very nice. Likewise, we get the dementia group difference specifically for the men. So that's lumping together the two contrasts that create differences across the three groups in the men, in the women, and we get an effect size for that. So now we're starting to get to the point where we can talk about what are the main effects of these variables within each group, and then refer to the interaction contrast to think about how each of those differences within each group, in the cells, not in the margins, are different across the moderating group. So estimate statements then to reiterate, so this is redundant with what we already got before for the sex differences within each group. That was already given to us right here. Then we have the pairwise differences, and those are buried in this giant table, if you take the time to suss them out. And last but not least, the interaction contrasts, which were not given in their full entirety above. Only two of them were given as part of the solution for fixed effects, which would have been right here, and this table is typically ignored in interpreting ANOVA output. So all the interaction contrasts then I have requested and given here with the same numbers that we've seen several times. So the moral of the story, when you have two predictors that are categorical, treated as categorical, meaning the program creates internal contrast variables and they interact, a lot of what you're going to get for your output is going to be marginalizing across levels of the other variable. That is likely not going to help you understand the effects because we need to dive into what the differences are within each variable, each unique combination, as well as then what those differences are. So your keys to making sure that you can dive in, simple main effects, not marginal main effects, for each variable at each level of the other, and then knowing how to get these interaction contrasts that give you each set of different differences that would be relevant. And as always, some words. So here is a sample output and sample equation that would describe how I would talk about all of these things. So the narrative here is taken from very much the same as chapter 2. I may have changed a thing here or there, but having a table and a figure would be essential in keeping track of all these parameter estimates and how they work together. So here is that. And that is the end of my story. Thanks for listening.